It is a pleasure to welcome you to the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is an pro bono initiative led by Dr. Partha Mishra and Professor Sarah Das. It is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. Today's lecture is on geohazards, which will be delivered by Professor Sarah Springman and Dr. Barnali Ghosh. Sarah Springman has been Professor for Geotechnical Engineering at ETH Zurich since January 1997 and Rector of the University since January 2015. She studied engineering sciences at Cambridge University. She then worked for 5 years as an engineer on several geotechnical projects in England, Fiji, and Australia before returning to Cambridge, where she earned her PhD in soil mechanics in 1989 and established an academic career. Her main interest in research is soil structure interaction and the geotechnical aspects of natural hazards, in particular landslides and melting permafrost. She uses geotechnical modeling to develop solutions that can improve the design of structures. Professor Springman has published numerous journal articles and monographs, as well as co-editing and reviewing submissions for a range of scientific publications and has given many keynote lectures. She has supervised 24 doctoral students, and has inspired many young women to take up studies in engineering and science. As Rector of ETH Zurich and within the Executive Board, she is responsible for education and as such for 22,000 students. She is in charge of admissions to study programs at all levels and for the organization and management of study-related matters.
Okay, fine, everybody. Well, and I want to share with you some of our experiences in rainfall-induced slope processes and failures. And you can see what beautiful scenery we have in Switzerland and some of the slope scenarios and challenges we face in Switzerland. We have high ground over 4,000 or getting to 4,000 meters. We have scale, accessibility, lots of rainfall, plenty of mass movements, rock falls, all sorts of erosion, and so on and so forth. So I just thought I'd share with you at the beginning just a few introductory slides just to paint the picture, if you like. And here is the map of Switzerland, where you can see in blue where we typically have floods, mainly in the river valleys, and in the middle plain in the Molasse-Becken basin in between the Jura and the Alps. We have quite often debris flow problems in the mountains and quite a lot of landslides that don't only restrict themselves, obviously, to the alpine regions. And there are various ranges of damage. I want to give you an example from the extreme storms that took place in August in 2005. And you can see a picture from this photograph on the left-hand side of all sorts of fairly small failures that occurred. And you can see on the right-hand side the brown dots and then the slightly increasingly larger green circles, the size of the volumes of debris. And one of the things that concerns all of us is naturally the amount of debris that is mobilized, because clearly the larger events have a far greater chance of causing much more damage. And just to put you in perspective, that's where we are in Zurich, up on the upper end of Lake Zurich. And I think my thinking in all of our research in these projects has been, what is the combination of slope angle, soil type? Does the depth to bedrock play a role? Does the drainage, how does the drainage play a role in the soil and even in the rock? And is there groundwater flow? Are there springs? And what role do they play as well? And this has driven a little bit the picture of how we might review the stability of slopes in the context primarily of the hydrological cases at the beginning. I've talked about rainfall induced, but we also obviously have impact of groundwater flow and snowmelt. We have then that causes effects in terms of the saturation in the ground, which affects the effective stress and also essentially in a rather old-fashioned term, the factor of safety. And how does the water get in there? Does it infiltrate from rainfall or from snowmelt? Is there saturated or unsaturated flow? What happens in terms of the drainage? Is it through preferential drainage, or is it in the matrix, and all of those things? What role does the geology and bedrock play? Obviously, that's pretty central as well. Is there any vegetation? Because clearly vegetation can be very helpful indeed. And then how does the slope deform? Do you have any warning whatsoever of a failure, and can you use that to manage the hazard a little bit in terms of the slope stability assessments and hazard management? How is it going to trigger? How is it going to move? Is it just going to slump? And this is very typical of unsaturated deposits, that it's not so mobile. Is it going to slide? Is there a preferential surface that it's going to slide on? Or is it going to flow, which means that effectively it turns into a heavy liquid and has much, much more run out. And again, the volume mobilized is important in terms of the hazard. So I'm going to tell you a little bit about some of the instrumentation and monitoring programs we've done, where we've used multidisciplinary methods, geophysics, and a little bit on remote sensing. And I might not get time to talk at the end about the numerical and the physical modeling. And we will show you some of the sites that we have instrumented. And in any case, I will supply the presentation at the end so that you will all be able to have a look. And I've put the references at the back, including most of the recent ones are open access, so you can see those without having to pay for them. Now, this is a very famous plot. It started from Kane in the 80s, where intensity is plotted against duration, and anything that is above this line is where a failure has occurred. And you will see that both scales are logarithmic, and there are lots of different predictions, of course, because they reflect the local conditions where these authors have been. And I think it's quite difficult, actually, to use a plot like this, because it really isn't terribly accurate, although I know there are quite a lot of people that try to, and if you're using it in your valley, maybe it might work for you. But I think there are so many things that affect whether or not a slope is going to fail, that actually intensity and duration doesn't really completely do it. And I think we need to bring in the knowledge from all sorts of different areas to understand better what the risks are, what the hazard is, in fact. So I'm just going to show you a series of pictures that we have available for us in Switzerland. I know this is not legible, but I've given you the reference in the notes so you can have a look. And what you can see here is that in the Alpine region here, we have typically soils that have been laid down under cold conditions. This is our what we call the middle land here, which are rather warmer, and you can see the blue ones are the fluviatile and so on, and you can have a look and see what are the typical surficial soils in Switzerland that are overlying the core geology. And here you can see, I'm going to show you both pictures, in fact, you can see going from the southwest to the northeast, these are the limestone heavily folded Jura and the tabular Jura. And in fact, I live just on the end of the Jura, just up here actually. So we have this amazing limestone outcrop, literally 1 kilometer away from where I'm sitting at the moment. And we have the Helvetic zone here in the Alps in this region here. And this is the so-called Mittelland, which has had all sorts of molasse sediments laid down in under salt water and under freshwater conditions in the past. And you can see all our lovely lakes here shown in blue. So, and there's a cross section here. So all sorts of complicated things going on in the Alps with folding and so on and so forth. I'm not going to go and give you a geology lecture here. But if we look at that now in terms of elevation above sea level, these are our highest points in the red, going over 4,000 meters. So the Matterhorn is somewhere down here, and you can see our lowest levels are around about just over 200 meters above sea level, and Zurich is here at about 400 or so. So that gives you a picture. You can see the importance of the rivers that are draining the high ground in each direction. It shows up very clearly on this picture. And possibly more relevant for us and helpful is the angle of the slopes, which helps us to understand where we will be likely to have floods and no landslide problems. And obviously a high of 78 degrees is in the rocky areas. So all of these are quite helpful, and I'm going to use slope a bit as an analogy for helping us to do a very quick assessment of whether or not we think we're going to have a stability problem or not. Now, this is a very interesting slide, and I had some help from one of my former doctoral students, Daisy Lucas, and she dug this one out. And it's worth having a look at. It has a one-day year two-year return level of millimeters, and they were derived from precipitation measurements at 360 stations in Switzerland over a period of 1961 to 2014. And what it shows us is that in the Italian-speaking part in Ticino, we seem to have the greatest risk of high rainfall. This is reflecting over the Alps here, and this is in the upper Valles, and the Alpine region here. In the middle land, it's really less of a risk, and then we're heading off at the lower end of the Jura here, again looking a little bit more serious. And these are in the black, these are the rivers, and these here are also the lakes. So it's helpful if you have this information. And today, Météo Suisse are moving on to always higher and higher resolution. So very shortly, they will be dealing in the order of squares of various meters rather than in 2 kilometer squares, 1 kilometer square, and all the rest of it. So down in Ticino here, we have a high performance computing center that chunks the numbers to be able to predict what's coming in terms of rainfall. And that is, in a sense, is our input. Now, I want to be quite simplistic about this. I'm not doing anything terribly complicated with critical state soil mechanics and highly complicated soil models, just to make it really very practical. In my view, if you have a drain slope that has an angle of alpha and you have a phi dashed of critical state or constant volume, then usually you will be on the edge of or in incipient failure. Unfortunately, quite often, we will see from our maps of slope angles, there are many slopes that exist with a slope angle that is greater than the soil's critical state angle of friction. And that's a fact. And it's not safe without suctions or roots or other measures that are holding it up. And that's always why whenever we have the massive rainfall, we hear about these sudden slope failures. And I think in a very simple model of C dashed and phi dashed, you can add in the C dash from some form of cementation between the particles, some form of root reinforcement, and some form of suctions that mean then that our Mohr circle is lying underneath this so-called failure line. And I think it makes it safe by adding this form of cohesion. I mean, we could argue if you want to add it to the friction angle as well. Talk about that in a minute. How reliable is it? How long-term is it? Well, clearly, that's all a function of the bonding in the cementation of the root, whether the roots will break or pull out, and whether the ground will saturate. And there is, of course, if you wish to follow very clearly the thoughts of Malcolm Bolton and the Cambridge lot about dilatancy, you can also refer to the fact that sometimes you gain extra strength from the interlocking of particles, and this is also temporary, because the moment you shear past the particles or break the particles, then it disappears. But you sort of have some kind of envelope, if you like, that adds up all of these things that gives you a boundary to help you explain why on Earth is a slope stable when you believe it probably shouldn't be. So let me share with you some of the sites of the field experiments that we've done in my group since 1997. And we've done on moraine in the Valles, on clay silty sand layers, on a silty sand in Rudlingen up in the north, and on a scree slope in the south. We've done all sorts of things. We've modeled, measured on a river levee and on all sorts of rock glaciers. I'm not going to talk about the river levee and the rock glaciers today, but just have a look and see the two sites in the northeast and two sites in the southwest are what I'm going to discuss. And I've summarized here with Daisy's help the instrumented sites and where they are located. Again, you can see the two in the top and the two in the bottom. And you can see the two in the top here are in the Melasse basin here, based on sandstones typically. They have really finer soils, clay sand, silty sand, or silty sand here. They're relatively homogeneous. They have rock at different depths, and we have vegetation and channels and reinforcement and all sorts of things going on. And in these two, effectively, we have a slope here for the first one, Tessex, which is flatter than the angles of friction. And in Rudlingen, it's much steeper, 38 to 40 degrees in comparison with the angles of friction measured in the lab. And then in the south west side, we have effectively two nominally scree slopes of different background. One is a moraine slope and one is really basically a scree slope, very well graded, angular, granular soil, very heterogeneous, all sorts of interesting slope in these case, one very much more shallow, one steeper, which ultimately failed, and so on and so forth. This one, again, not quite so critical. So I'm going to show you some examples from all of those in the next few minutes. So the first one is in the forefield of a glacier. It's above a village called Sassbalen that in the past has had, in the 60s, had nasty debris flows emerging from these little lakes here that were in the forefield of the glacier. If we look at the right-hand side, you can see this is where the Gruben glacier has shrunk to, but this is sort of the forefield here. This is the lake here. This is all permafrost. And it caused really very nasty hazards for the village, and they built a weir in the front here of the lake. And we're going to look at this part of the moraine bastion in front of the lake, and you can see here it really looks a bit like a bomb site, doesn't it? Very heterogeneous soil conditions, but it has a significantly fine fraction of silt that means that it holds suction. This slope is 31 degrees, and we instrumented an area of about 100 square meters. We also had one of 42 degrees. That was in the second year with a smaller area, and that was very difficult to work on. We pumped down water from the glacier lake to spray all over the area. The ground itself was so actually quite medium dense, interestingly. We did a huge amount of laboratory testing, including 25 centimeter in diameter and ½ meter high reconstituted samples of moraine. That was very interesting. And in situ shear box tests and all the rest of it. The papers are actually here mentioned at the bottom and are quite well worth having a look at. And we put in place all sorts of ways of measuring volumetric water content, and we measured, of course, the rainfall intensity. And in this case, in the first year, we did the experiment over 1 week, and we applied, here is the rainfall at the bottom. So it was a little bit of an experiment at the beginning, then a pause, and then more, and then a pause, and then fairly consistent for 5 days with a minimum level of 10 millimeters per hour and going all the way up here. And as my colleague from hydrology said, "What, Sarah, you want to make the mountain come down?" So it was a pretty extreme rainfall event, they said to me. And you can see this is a moisture point device that averages out the volumetric water content over the top 15, next 15, then 30, 30, and 30 centimeter lengths. And what you can see at the top here is that now calculated as a degree of saturation quite quickly. The top 15 centimeters got gradually saturated, then there was a pause and it unloaded, recovered, increased more, unloaded, and then gradually, and it got up to just over 90%, even after a really incredible and lengthy rainstorm. And then the next ones were 15 to 30, 30 to 60, etc. And at the lowest level, it only really got to about not even 40% of saturation. So it really was quite clear that it was a top-down saturation event. Unfortunately, in the first year, because again, we were working just under 3,000 meters above sea level, and it was our first lot of experiments, our tensiometers didn't work. We did better in the second year. And in the second year, we only had a 2-day event before we had a failure. But I think this is quite nice to have a look at the suctions again over the time. So the rainfall started here and finished here. And you can see that at 30 centimeters depth, the first reaction occurred. And then, oh, sorry, at 16 here, the first reaction occurred, then at 30, and then at 40, but we still had suctions of about 5 kilopascals, even after a couple of days. Probably, maybe if it had lasted a week, those would have completely dissipated. But very nice data to allow us then to summarize everything together for both periods, to say that here we have with depth the saturation degree from both years, from all of the different devices, the TDRs and the moisture points, showing at the beginning of the experiment what the saturation degree and the slope was and what here at the end. And so we can see for the upper half a meter, this is what it looked like in both of the years, very consistent in fact. And here you can see the suctions going from the right to the left at the same time. So again, very useful data that gives us an in situ understanding of saturation with depth and what that means then for the effective stresses. And I'll come back to that a little bit later. I'd now like to introduce the next site, which is on the River Rhine. Some of you may not have realized that the River Rhine actually comes into Switzerland. Mostly it's on the border with Austria and Germany and France. But here we had, in this morass basin in the northeast of Switzerland, we had effectively in May of 2002, we had a 10 centimeter rainfall event in 40 minutes and 42 superficial landslides. Now, some of you may know I'm an athlete and I used to row a lot. So I used to row my sculling boat along the river here, and I'd see all of these. This was the lovely view before the failures, and here you can see some of the small failures and that occurred in this region. So of course, being a researcher, I was asking questions. First of all, why? And secondly, of course, as an engineer, how can we help our colleagues? So we started off with this site in Tessex, and we ended up with the site in Rudlingen. So I'm going to tell you a little bit about the Tessex site. Here you can see the picture of the Rhine flowing down and these wooded slopes here, this for agriculture. And we're going to look at this slope here where Andrea Thielen set up a very interesting 3-year monitoring experiment. And here you can see the site a little bit closer. We had a MET station here. We had 4 different instrumentation zones in each of the corners where we had TDRs, we had tensiometers with a pressure sensor, and we tried to measure runoff and all of the other things that you would imagine. At the top here as well, we had a piezometer to try and understand what was going on in terms of the groundwater. Unfortunately, we weren't able to try and measure ground movements. We had tried in Gruben, that hadn't worked. But again, this was not a slope that was expected to fail. In fact, the farmers would have killed us if it had. So we worked very closely with some colleagues in geophysics to try and understand what the ground profile was. And you can see from the different pits that we installed to install the instruments that we had topsoil is in green. We had a clay sand in brown. We had a silty sand below that, and sometimes we found bedrock. And you can see here the combination of the TDR probes and the tensiometers at each depth, so we could do effectively produce a very nice water retention curve at each depth. And as a result of our diggings and our geophysics, we produce this profile here showing the rock again flattening off towards the top of the hill, and we decided then to do our experiment in this region here. And working with Sven Friedel, a geophysicist, we did some very interesting monitoring using electrical resistivity and over periods of time. And one was in the summer of 2003, and another one was a summer a year later. 2003 was very dry. 2004 was quite wet. And what you see from the resistivity here is that where it's very blue, you can say the resistivity is low and the ground is quite saturated. So you can see that underneath the top surface of vegetation and of the clay sand, in the silty sand layer, which obviously was more permeable, you could see that there was water was reaching through into that and causing potentially a hazard. I should say here the slope was only 27 degrees and our test field was in this region here. So actually at the end of the day, it wasn't a huge risk, but it was very interesting to monitor over a period of 2 years. And just as an example, this is some of the data. We didn't really have very much rainfall, millimeters per day. You can see we had one storm of over 15 millimeters a day, but otherwise it was really very, very small. And what you can see from the volumetric water contents in gray and from the suctions in red, you can see that obviously they're reacting. You might have a high volumetric water content and a relatively low suction. And then there's a kind of a flip into a summer season behavior around about May or June, where the ground drains and the suctions go up. And we were able to measure that and record that over the site, and then produce predictions on the factor of safety for the site. Introducing Rudlingen now. This Tessex was down here, just up the river here. This was our test site. I was absolutely desperate to find somewhere where we could do a formal landslide experiment. And we found this place here in the woods. And you see here a very Swiss site. We had steps on the side. We had lights. We cleared it. We instrumented it in a similar way to our other sites. We had a net on the bottom because there was a road down here. We tried to measure runoff, all sorts of things. It was a very, very extensive experiment with lots of different doctoral students from different colleagues. Armin was my doctoral student and did a fantastic job in leading them all. And as you can see, it was quite difficult to find somewhere. Here we see, because of the bendy trees, that clearly there was creep going on over a period of time. It was a vegetated slope of 38 degrees. We eventually discovered with, again, Francesca Cassini was a postdoc, did lots of work on the soil properties. And so we thought, well, here we must be able to make this fail. There's a huge amount of organization in order to make it work. But it was a fantastic experiment. So here we are. Here is a cross section from Armin's work. Bedrock was a bit variable across the site, but ranged from about 1 meter through to getting on for 5. And we did, again, lots and lots of experiments to try and characterize the ground. Typically, in our different clusters, we had 3 clusters up the slope here. This is about 8 meters across and about 30 meters in length up the slope here, with the barrier at the bottom and the road here and the Rhine down at the bottom. And we installed these devices at 15, 30, 60, 90, 120, and 150. That is what we used. And Armin designed some in-house deformation inclinometer probes to pick up on the deformation. And I'm not going to talk about those today, but there's some really interesting data there as well. We had piezometers on the bedrock and all of the other things. We tried with some acoustic sensors, and this is was very interesting at one stage as well. One of our colleagues, Massimiliano Schwarz, did a mapping of the roots. Here you can see in one of the bedrock, and Peter Kienzler did some infiltration experiments so we could understand a bit how the infiltration worked. This is the bedrock here on the bottom. And this is now a plan on the slope. This is the top of the slope here. This is the bottom of the slope here. This is the road down here. And he mapped a kind of equivalent apparent cohesion from the roots. So the brown circles are the trees. And you can see in our slope here that there was much less cohesion at the top of the slope than in the bottom. And somewhere in the middle, on the right-hand side of the slope, was this great tree that actually made a big impact on the way the thing failed in the end. Okay, so we had an attempt to try and fail it in October. We didn't succeed even after two meters of rainfall, but we came back in March. We made some changes, and we had the clusters at the top of the slope, in the middle, and at the bottom of the slope. From the moment the sprinkling started, we could see that saturation was occurring. It was interesting, a little bit at the top, but mainly from a bottom-up saturation approach. And that has something to do with the geology here. This is the upper seawater sandstone and the lower freshwater. And in the bottom section, there were these massive fissures that actually, when we tried to rain on the site, we had a borehole at the top too. When we tried to rain on the site, it meant that this drained the ground from below. So it's a bit like trying to fill up the bath when you don't have the plug in it. And that explained why our first experiment didn't work. And we have supplied the water from the top here, from the hydrant, and having worked it out that we had all of this lovely drainage going on down in the bottom part of the slope because the water was flowing out onto the road at the bottom, we realized we needed to move our experiment a little bit up the slope to try and force a failure. And then we discovered, because of the impermeable layers of rock, that there would be exfiltration occurring, and that was a very important part of what was driving the failure. So I want to summarize this very first part of the lecture by saying to you, here we have the three different cases, and these are my sketches that pretty much summarize what I think went on. In Gruben, in the moraine, we had a saturation from the top down, from the rainfall. And we had, in the end, we had a very shallow slip for the case where the slope angle was greater than the friction angle. I can show you that in a bit more detail later. In Rudlingen, we had a very complicated system because we had drainage in the bottom part here. And when we rained on the slope, we were able to end up with a saturation both top down and bottom up in this upper part of the slope. And we ended up with a failure up here. Whereas in Tessex, where we had the two layers here, we had a sort of a summer regime that was, again, similar to Gruben here, was a top-down saturation through this clay sand. And in the winter, we had a kind of also a bottom-up saturation in this slightly more permeable silty sand layer. So I think understanding these saturation mechanisms are really important when you're trying to appreciate what's going on in a site and whether or not you have a risk. Now I'd like to move on to the last experiment, the Morecibak catchment, which is a very interesting site. It's next door to this highly active catchment that produces rock, that produces debris flow material almost on an annual basis. And this slope here was a scree slope, was above this village called Agarn that from time to time has experienced debris flows. And they put in place all sorts of measures to stop any of the material reaching the village. And in fact, that has worked quite well. But this scree slope presented an interesting challenge alongside the debris flow behavior in the active channel, which was looked at by some colleagues. And here you can see the scree slope. You see this lovely character here looking at what on earth we're doing with our various instrumentation. And we worked together with colleagues in geophysics to try and understand what was the depth to rock, and also to do a little bit of monitoring of the slope as well. And Daisy dug some instrumented trenches, 1, 2, 3, and 4. We installed some cameras and snow stakes, and we did some density tests and ERT profiles, and of course we had a MET station as well. And that was a very interesting experiment. This is the first preliminary results from the geophysics from the ERT. Also did some very interesting GPR work as well. And what one can see again here is based on the resistivity, the blue being the more saturated, dependent upon the weather conditions, slightly cloudy, drying out, lots of rainfall. You can see again saturation from the top here, and what's the difference between these two and these two shown here. And at the end of the day, together with the GPR, this is again the scree slope here, and picking up on the depth to bedrock over the whole site. I'm sorry, this is a bit small at the bottom, but the deepest depth to bedrock was in this zone here of about 2.4 meters. So typically a lot of it around about 1 meter in depth. And again, in a slightly challenging environment near to 2,000 meters above sea level, the experiments were running over a period of from the November of 2013 to November of 2016, so for a 3-year period. And the 4 pits were completed at different times, and sometimes there was a break in data, of course, being up in the mountains. And the volumetric water content is on the top, and then the temperatures here are on the bottom in each case. And at the bottom here we have temperature and we have rainfall down at the bottom. And it's quite interesting just to see the trends. The blue bits are the winter, and the yellow bits are the summer. So again, this flip, just like we saw in Tessex, between the behavior. So in winter, temperatures showing around about 0, sometimes below 0 here, and that causes a drainage in the ground. And then in the summer, where the temperatures go up and there is rainfall down here at the bottom, you can see very responsive again to the rainfall. And we always, just like in the first site, Gruben, everywhere else, we get a sort of an exponential recovery in between, so dropping off very quickly and then building up and responding very quickly indeed as well. So this has been published in a recent paper, again, open access if anybody wants to study that in a little bit more detail. The impact of the snowmelt is also important as well. So there's a lot of data there, and I don't want to try and explain every single different point to you, but it's worth having a little look if you have a site that is similar. So now I just want to come on to the mechanisms of failure in the 2 sites that failed. That's the Rudlingen one that was sort of ready to go, but I'm going to come back to Gruben first of all, which happened when we weren't actually on site. You can see here the instruments that have been destroyed, and this was on this steeper field, the 42 degree slope. And the measurements in this slope of the TDRs, of the volumetric water content that we turned into saturation degree, starting at 70% at the beginning when the rainfall started, until up to here when the rainfall occurred again. TDRs at different depths, so we had sort of anything from 85 to 96% of saturation. Then suddenly there was this failure, probably at about 0.2 meters in depth, although that also wasn't entirely clear. And if you did the sums on a very simple infinite slope approach at the beginning, you would say the factor of safety was over 7 at a depth of 0.2 meters, and clearly it was 1 at that moment in time. So losing or increasing your saturation by 20+% had made a huge difference in whether or not this layer was stable or not. Coming on to Rudlingen, we knew from the October experiment that in the top right area of the field there'd been some movements. So we knew that it was probably going to trigger in the top right. We knew the path were probably on the right-hand side, standing from the bottom of the slope, looking up the slope, and that the run out would be into the net in the bottom half. And I'd estimated 150 to 200 cubic meters. But I have to say, we did that quite well, but we were absolutely useless about when it would fail. And you can imagine it failed earlier than we expected and at 3:23 in the morning. So that wasn't quite what we had wanted. And we averaged the sprinkling to move up the slope. We sprinkled for 15 hours at an average of about 10 millimeters per hour. And the papers tell you all of the details if you're remotely interested. So in the top part of the slope here, you can see the rainfall here at the bottom. This is the rainfall intensity here. And you can see the reaction occurring first at 60 centimeters, then the green is 90, the mauve is 120 centimeters, and then the black is 150. And you can see again that there was a mixture of top down, and then here this one was showing definitely a bit of bottom up response. And when we looked at the piezometers that were placed at different depths, this was at a depth of 3 meters here, there was one at a depth of 1.4 meters further down the slope, and you can see that what happened then, that there was a water table that was building up on the rock, the bedrock here, and it reached probably about 1.6 meters. So that was sort of showing a very strong bottom-up saturation occurring in the upper part of the field. And so that was the field beforehand, setting it up, and that was the field here afterwards. So the failure occurred in this top right-hand side. There was a lot of exfiltration happening on these impermeable soil layers. These were the deformation measurement devices. This was this tree that really stopped the failure here and channeled it down in this direction. And I hope I can maybe try and show you now the photogrammetry data that gives us, it's not, the resolution isn't quite so wonderful, but it gave us the ability to analyze. And look here at the top right hand side of the slope, we had ping pong tennis balls inserted into the slope so we could pick the failure. Here you can see the fissure opening up, shearing on the sides and on the bottom. Here you can see the exfiltration occurring. It took about 36 seconds to get to this moment, and then the last 12 seconds to dash down into the net at the bottom. So here you can see the exfiltration occurring, and we had a couple of our deformation probes in the top, which meant that it was possible to pick up on how the failure developed. And that's very, very well worth looking at, and thank goodness we had the lights to be able to see that. And that was a big thank you to Devrim for doing the homework and Armin for making the picture. So here you can see the effects of the roots pull out on the side and breakage there, but they, together with the suctions in the slope, had been responsible for keeping this 38 to 40 degree slope stable, even if it had been creeping at different moments in time. And coming on now to Daisy's experiment in the Marechibak, the scree slope here, just in behind this active channel where the debris flows form. Actually, this was not really at any great risk of a massive failure other than possibly a deep-seated landslide. There was a lot of small events going on, from toppling from the rock walls behind, from individual rock falls, and lots of raveling. So it was very much a gravity-driven process. But the thing that we'd been worried about in terms of mobilizing a rainfall-induced landslide and depositing debris down into the forests above the village of Agam below wasn't really found to be such a major challenge. But there was a but. If we had a step in the bedrock, which we saw as a result of the geology sometimes was happening, then you could have a raised water table here, and you could then have an impact. And I'll show you a little bit about that later on. Now, I realize I've gone on probably too long. These lovely pictures of the numerical modeling and some of the physical modeling I'll leave in the picture at the end. This is of the Rudlingen, recent paper with colleagues Panos Sitarenos and Francesca Cassini. Have a look at those if you're interested. This was Daisy's work in the centrifuge, picking up on how you could create such failures if you had a step in the bedrock here, numerical modeling as well, depending on the steps, what that did in terms of the volume of the failure, failed material. It's all there. And I think I'm now going to come on to some conclusions, if I may, and just say in summary, in this case here, this was a top-down saturation. A shallow slope was never going to fail, but it did occur in the 42-degree slope, and it was all fairly consistent. And this was what started me off in my interest in rainfall-induced landslides. So again, in the Tessex, it was a double-layer system. The only way this slope was going to fail was if there was water in the underlying layer under pressure that caused effectively uplift pressures on the upper layer, but we had a summer regime and a winter regime, also very interesting. In Rudlingen, we had a huge amount of instrumentation. Without the suction and the roots, it would never have stayed stable. We had mainly bottom-up saturation here. We had amazing drainage in the bottom, and we were able to work out where the failure was going to occur, but the when was a disaster. And that's really what we need to work on now. And I think what it also showed was there are all sorts of interesting remediation opportunities with vegetation and with drainage as well. We all knew that anyway. And then in Daisy's slope, again, a very steep slope, not likely to fail in the normal sense, but if you have funny things going on with the geometry of your bedrock, you could end up with some local failures, and it enables us to assess hazards holistically for the village below. And on that note, I've got about 10 minutes for questions, and I'm going to shut up now and hand back to our colleagues. Thank you very much for your attention.
Thank you, Professor Springman. So the first question comes from Amir, and he basically would like to ask if you can suggest some cost-effective solutions to mitigate slope instability in small residential projects and houses in similar conditions.
Okay, well, I think the key thing is how does one get rid of the water, and how do you maintain the slope in an unsaturated state? If you can vegetate it as well, that's important. And I think also, for heaven's sake, don't build in your housing in a region where your slopes are steeper than the angles of friction. And you saw from the case where we did a very simple sum on factor of safety, that when the ground was dry or there were suctions, we were at a factor of safety of 7. Let's make sure that in the case of your housing estates, the factors of safety are always in those regions. So just like you don't build houses in a floodplain, try not to build houses in an area where the slopes are really much steeper than the ground. And if you have to do that, then you have to find ways of reinforcing it in some way.
Let's take the next question. And this one comes from Dr. Lewis, who is at ETH University in South Africa. He says that you mentioned about difficulties in predicting the exact movement of one of the failures. And then he wants to ask that in hindsight, can you explain when the failure occurred, when it did?
Okay, good. Yes, we can. And we go into that in really quite some detail. And I think when you look at the deformation sensors, they show, first of all, some movement in the ground at 30 centimeters and then down at about 130 centimeters. So actually, if we'd been watching that, and if we'd had a very extensive early warning system combining information from the rainfall, the saturation degree, the movements in the slopes, you would probably have been able to predict that you were getting into a difficult situation. The challenge you then have is, do you evacuate the village below? And if you do it too many times and nothing happens, you have the issue of crying wolf. So that's also very difficult. So then what you might have to think about is to do what they've done in the village of Pontresina in the Engadine, where they've built this huge dam that will trap any material that comes down in terms of avalanches or debris flows, and so that you have the first reaction is able to absorb that. And again, in Agarn village, they have an absorbing channel. They have a huge reservoir which will absorb the first push of the debris flow material, and they have measurements on the streams to see where they have a debris flow starting. And then you've won a little bit of time and also a bit of patience from the inhabitants who are not permanently getting up at 3 in the morning and leaving their beds because you're worried that the slope might fail. So we as engineers have to try and make a better prediction of when we're near to failure. And I think actually the moment of failure is harder to get, but you will see from accelerating movements often that something is about to happen. And I think that's I think that might be helpful. But it's work for the next generation to do. We haven't solved it yet.
The next one comes from Ian, and he says that at Tessex, with the silty sand confined by the overlying low permeability layer, was there a potential for static liquefaction that may have led to the failure?
It could have been, yes. But as you saw from the rainfall records, we had one day in the period of time with about 50 millimeters in the day. And you saw in the Gruben case how much rainfall we needed to add up over a week to even try and saturate the ground. So I think in principle, yes, if we were in monsoon conditions or something like that, possibly that slope wouldn't be there anymore now. But in the sort of relatively temperate climates in Switzerland, even with the effects of climate change, actually we're not going to be under too much threat. But if we have very, very extreme and long-term rainfall, we will see more slopes that will be challenged, I think, too.
The next question, I think there is a commonality between some of the questions. That's around which geophysical methods you go with when you choose to monitor a site. For example, there are GPR, there is ERT, there is TDR. So there are some questions which ask around that how do you select which method?
Okay. I am not an expert on geophysics, but I love working with my colleagues. I've done it in permafrost, all sorts of different methods. And what we do is we try and work out what we're trying to find out. So if it's characterization, so there's a characterization, there's monitoring, and there's modeling. And we can do that all the way through in the geophysics as well. And if we're coming along to a site and we absolutely don't know what's below the ground, then of course we do the classic geotechnical approach. We do the desk studies and all the rest of it. And our colleagues will help us and say, right, there is ice in this slope. Therefore, we'd be better to do seismics, or we can monitor what's happening in terms of the change with the ERT, or the GPR will give us an understanding, depending upon the resolution we need, exactly what we need to do to get us the bedrock. So just like our own geotechnical methods are focused on what we want to find out, we do the same thing with the geophysics. So we work hand in hand and we involve them right from day one. They are partners at the beginning of the project. They're co-applicants, and everybody is at the same level, and that works very well. And again, what we've seen too is how instrumentation has evolved. In the very early days, we were doing the inclinometer measurements on the rock glaciers with the tilt meter that went down the hole. Now we have the shape array Excel that allows you to pick up and measure movements in the slope. And if we haven't had our own instruments, we've developed, if we haven't been able to buy them, we've developed our own, again, like these deformation probes that were based on an idea I'd had from centrifuge modeling. of a 4 centimeter wide and very thin, so that it would bend with the slope. You could put strain gauges on both sides, and you could pick up then where the ground was moving. That we never turned into a spin-off, just a little bit difficult to do, but again, for a very shallow bedrock, that would be something that other people could develop and use as well in the future. So you just have to use all of the information that you have, pull it together. What do I want to do? Be creative about it, and again, work in a multidisciplinary group. Also, for our colleagues doing different forms of remote sensing, whether it's photogrammetry. We've done work with LiDAR on rock glasses. We've done work with terrestrial interferometry, and they've been very revealing. So you just need to involve the right experts and come together as a team, and that helps you to understand in a more holistic way how your slope is behaving. And once you've built up this knowledge, you can sort of do a bit more smart prediction later on of where you think it's going to go. And I think my answer to the question about Rudlingen was that I have to say, trying to run an experiment like that was a massive load, and trying to have it all going on at the same time. And what I regret were 2 things. One, that I hadn't run a little bit more modeling with Armin in advance, so that I hadn't gone to bed at 2 o'clock in the morning when the failure happened at 3:23. And also perhaps that then I might have, instead of being anxious about not getting to a failure by the end of the week, which was our worry, that one would have done it in a more stepped way, a little bit more controlled. And however, but those are things that happened in the past, and it's been a very interesting experiment from which many people have learned, and it's fed in also to the hazard management from the canton of Schaffhausen, which is where the site is located.
This one is particularly interesting because it has a social side to it. So Alison mentions that in Uganda, it is difficult to get people moved from unstable places. Vegetating the place has essentially helped, but it still occurs. So how best do you think that the engineering practice and the social work, these government restrictions can be used in African countries to prevent death and destruction that are caused by these unstable slopes?
Here you would say, "Bof, ich bin überfragt." I'm probably a bit over my head on this. We have, what I can simply say in Switzerland is we have our cantonal offices who are responsible for these things. They have hazard maps. And in terms of the planning, the town planning, they say you cannot build in this area if it's a red zone. They have certain ability to move people out if it's in a red zone, but if it's in a sort of an orange zone or whatever, it's much harder. And so in a place like Uganda, I'm not sure what the formal rules are, but I also aware, having lived in Fiji, that people will ignore them anyway and just do what the heck they want. So and the problem is that people will live based on what their day-to-day experience is. And if the day-to-day experience is this slope has got a factor of safety of 7 because it's not going anywhere, it's not moving, I don't see anything, why on earth shouldn't I use it? Because I'm desperate to grow food and whatever, then I think the only thing you can do is education. And you can say, if it rains, these are the things you have to look out for. And if it rains, it could suddenly have this very dramatic failure. That's when people can't get away and save their lives, because saving their life is better than if they lose their house and their property, which is incredibly sad, but better that they can save their lives as well. So again, I'm a little bit out of my depth here, but trying to extend from what we have in Switzerland to what might be useful. So again, using the early warning system of information education, this is what to look out for. And when it's not doing it, you're fine. Yeah, and sometimes they use slope management practices that also reduce the factor of safety if they're wanting to water the slopes and do whatever. So it's trying to understand the system, and we as geotechnical engineers should try and be able to quantify a bit the risk, and then try and work out whether on the social science side, whether we're able to influence people and whether we need to influence people.
Okay, we have a lot of questions. We'll take perhaps this as the last one. So for example, in an engineering project, we have a budget. And then when you have a budget, what methods would you recommend are the most important when you're looking at slope stability analysis?
Okay, so I think we need to understand what's happening on the rainfall side. Very often we have local measurement systems, so you can use something that is relatively simple. I think you have to understand what's going on in terms of the volumetric water content and the suctions. I think those two are essential. It's like our water retention curve in situ that matches also the water retention curve that you can get in the lab. And if you can stretch to an inclinometer of some way, shape, or form, so that you know when there is movement, even at the surface, simple surveying systems people are using these days, which can work 24/7, and you can have the message coming on your mobile phone when something has accelerated. I think that's a very cost effective. If you have a chance to have an inclinometer, that costs a lot more. But I think, it's always difficult, and you have to weigh up the pros and cons, and each slope will be different, will present different challenges. And I wish you all the best. I have to say, we've had same questions for all of our experiments, more or less. We haven't ever had a massive extra budget, and we've cannibalized past instruments from previous sites and put them in the new ones to try and make them work, as I'm sure everybody else does on a daily basis. So thank you to all of you for being there. I'm very impressed that so many people turned up on what is apparently a bank holiday in Queensland. Thank you for being there and asking all the questions and joining me in Zurich. You can see the lake behind me, and you can see my campus below, and the main building is somewhere down in where I spend most of my time now. So it's been lovely to join you and come back and play being a geotechnical engineer for a while. Thank you.